Hi, today we have our first lecture on scientific thinking. You probably ask me why I'm not using my slides for my today's presentation, because I think that today's presentation I can just simply talk to you about major things that we use in sciences and in biological sciences including. So today is only one lecture that I'm not going to use my slides. I'm going to just talk to you. You can look at the slides later and you can connect my talk with the slides that I posted. So let's start with understanding what is scientific thinking and why we're talking about it as the beginning of our whole course of biology, introductory biology course. So what's the difference between science and mathematics, science and math? Why do we call science is what? Chemistry, physics, biology, and other sciences, but mathematics stands aside from the sciences. So the major difference is the sciences are based on what's called empirical observation. So what is an empirical observation? So empirical observation is experimental observation. So sciences, differently from mathematics, are trying to describe the phenomena that are observed, experimentally observed, or observationally observed. And that's what's called empirical knowledge. So empirical knowledge is based on observation. Mathematics is based on logic. With the help of logic, you make connections between two objects or between two phenomena. That's logical conclusion, and typically it's 100% proof. In biology, nothing is 100% proof. It's proved only with the probability. We can say with a certain probability that observation is correct, and that's what science is. Makes sense different from mathematics. But science is using the tools of mathematics. So don't get me wrong, we need mathematics. So science is observing things that make sense, and based on certain observation, the scientists make a prediction that two events might be related and connected. For example, the drug works, and that's an observation. Now we have to hypothesize that the drug works, and then we have to design the experiment that will prove that the drug works, and then we have to make data to show the public that the drug works and sell. So that's what scientists do. Scientific thinking is very critical for us. We have to be open-minded. So another, I would say, synonym for scientific thinking is called open-minded thinking. So being open-minded, what does it mean to be open-minded? Being open-minded means that if somebody with scientific data show you that your knowledge is incorrect, and they can prove it with the scientific data, you should be able to change your mind and accept scientific data that disprove your previous beliefs, or you would think they're not. So even Dalai Lama, number 14, said, if, I will quote, if science proves some beliefs of Buddhism is wrong, then Buddhism will have to change. So what does that mean? So that means every knowledge that is you think is absolute knowledge, you should be able to change that knowledge if you have enough scientific data that proves that that knowledge is incorrect. I hope that is understood. So right now, what is scientific thinking? Scientific thinking is when we have the theory that we want to prove, we have to, based on our observation, we should design the hypothesis why we think those two phenomena are related. So let's say, based on current exposure of COVID-19, I'm going to use the COVID-19 as an example for you to make you understand what is scientific thinking, what is hypothesis, what is experimental design, and what is anecdotal observation, and what is science or pseudoscience observation thinking, and what is proven hypothesis and what is not proven hypothesis. So you probably know that currently we heard a lot of stories about hydroxychloroquine drug, anti-malaria drug, that some anecdotal observations coming from some doctors suggested that it might work to treat COVID-19. So anecdotal observations were coming from several doctors who were giving their patients hydroxychloroquine, and they said it worked. It improved the quality of the disease, or the quality of the patient with COVID-19 when those patients were given COVID-19. And some patients said, "Oh, I took of that drug yesterday, and today I already feel like a healthy person." So those are observations called anecdotal observation. So when scientists wanted to make sure that the hydroxychloroquine worked, so they decided to look at the data and compare the data scientifically with the design of control and experimental group of patients where this drug worked. One paper was not published the data that did not have a great design. So, and when the other scientists and doctors look at those data, they show that the experiment was not designed correctly. In that particular paper that was published in the Journal of New England of Medicine, showed that hydroxychloroquine actually was more harmful than even helpful for COVID-19 patients. But then the scientists showed that the design was not incorrect, and when somebody did with better design, they showed that hydroxychloroquine does not make any harm, but it doesn't help either. So, so here we have the example of everything: pseudoscience, anecdotal observation, and experiments that was done incorrectly, and experiment that was done correctly, but still we don't have enough numbers to show that the last experiment is correct. We're still looking and waiting for more data coming from this hydroxychloroquine. Okay, so again, good design includes observation, hypothesis, prediction, experimental design, and conclusion based on analysis of data. In your textbook, we are actually having a great example how to do analysis of the drug only based on this medicine to treat common cold, and it's out-of-the-counter medicine called echinacea. So echinacea was thought to be useful to treat common cold, but when the experimental design was done correctly, it's been shown that it doesn't have an effect. So in your textbook, you can see how the scientists who did this experiment designed the hypothesis. You need to know what is working hypothesis, what is null hypothesis, null hypothesis in this case. So the hypothesis would be that echinacea is effective drug to prevent or treat common cold. Null hypothesis would be that echinacea is not helping with the cold treatment or prevention of the common cold. That's called null hypothesis. So the experiment was designed the way that the control group included the patients that did not take any drugs, or to have the patients who did take the drug called placebo. So placebo, it's a drug that people think that they take a drug, but actually there's nothing in that pill. It's an empty pill. but they think they take the drug, it's called placebo. And the experimental group that was getting that echinacea as the medicine. So when they compare those data, they show there's no significant differences between treated and control groups. So the anecdotal observation that this medicine works scientifically was not supported. So there's no scientific support of this data. So when scientists do experiments, they have to design experiment correctly. So they have to find the control group and experimental group from the same type of population. For example, I'm taking patients from 3 different areas. One, let's say, from Atlanta, from Sandy Spring, from Stone Mountain. So all these people are coming from different groups of people. And let's say my control will include all 3 populations. In my experimental group also will have all 3 different groups from all 3 different cities included. So it's called randomized test. So the test have to be random, randomly chosen patients, randomized. In addition to be randomized, experiment has to, the good experiment has to be blind. The blind means that the patient that takes the medicine doesn't know if he takes placebo or it takes active drug. So blind experiment, the patient does not know what it takes, placebo or the drug. And double-blind experiment is even better because not only the patient doesn't know whether he takes the drug or he takes placebo, the doctor who is analyzing data from that experiment doesn't know who is taking placebo, who is taking drug. He just has those random numbers. So and then eventually he will know who was taking what, but those numbers, people that the double-blind experiment, the researcher does not know what those numbers coming from the control group or experimental group, double-blind experiment. So with this, I'm gonna finish my short introduction to the experimental design, scientific thinking, and I hope in your future life as a scientist, as the scientifically educated people, you will be always able to be open-minded and think critically and request the data. If somebody tells you something, ask for the data and don't believe anecdotal evidence.